Okay, morning everyone. It's my pleasure to introduce our first speaker for the day, Zhenkun Li from Stanford University, and he'll be telling us about Instanton Floer homology and Heegaard diagrams.
Okay, thanks for the introduction. Thanks for the invitation. It's great to be here. So today's main topic will be Instanton Floer homology. So it's a homology theory for three manifolds and knots. Right, so in particular, so there's if we have a closed oriented three manifold, then we can define its Instanton Floer homology. And if we have a knot K inside the three manifold, this is a knot, or if we have a balanced suture manifold, right, so in each of the three cases, we can define the corresponding Instanton Floer homology associated to these objects. So the Instanton Floer homology is a finite dimensional complex vector space. So I guess people are more familiar with knots and three manifolds, so let me roughly explain what is a balanced suture manifold. So it's a pair M and gamma where we have a compact oriented three manifold. And this gamma is a closed oriented one manifold on the boundary of M. Another no one. It's a little hard to see, okay? So let me try another. Yeah, this looks better. And this manifold on the boundary of M. Great. Yeah. So so that, well, we have some conditions on this angle. I'm not going to say that in detail, but essentially we want this curve or this so-called suture that divides the boundary of M into two parts of equal characteristic. Right, so there are some basic examples for balanced suture manifold. So for example, if we have a closed oriented three manifold, right, so what we can do is we can figure out a three ball out of this three manifold, and then we take delta to be a connected suture, where delta is a simple connected curve. On the boundary. So this curve will divide the boundary to the two sphere into two disks that those are the same Euler characteristic. And second basic example is that if we have a knot inside a suture inside a three manifold, right? So this is a knot. What we can do is we can take the knot complement with two meridians as the suture. So gamma mu, this is two meridians. Okay, so if we have two meridians, that will divide the boundary to the power into two annual lines that equal characteristic. So these are the basic examples for which we have suture manifold. So it's a work by Brunheimer and Morocco. And they constructed the sutured Instanton Floer homology for any balanced suture manifold. So if it's given any balanced suture manifold, there is a sutured Instanton Floer homology, which we write as HI of the suture manifold. This is the sutured Instanton Floer homology. And as I said, well, it's a finite dimensional complex vector space. So here we have the constructions of a balanced suture manifold out of a three manifold or out of the not inside the three manifold. So we can define accordingly. If we just have a three manifold, we define the frame Instanton Floer homology to be the suture Instanton Floer homology of this suture manifold Y bracket 1. And we also, if we have a knot, we define the Instanton knot homology to be the suture Instanton Floer homology of this knot complement with the particular suture two meridians. So this is the frame Instanton Floer homology. And the Instanton knot homology. So this Instanton theory is very useful. So it has many milestone results, which is proved using this Instanton Floer homology in the setup. So many great applications involve, for example, it can be used to prove the property B conjecture. And also there's other proof that Pavilion homology detects N naught. And both of them are work by Brunheimer and Morocco. And of course, well, after the first result that Pavilion homology detects the N naught, there's many follow-up results like detecting triple by Baldwin and Ye, and also many following results. So this is why Instanton Floer homology is interesting, and so they're interested in studying its properties. So the main result I'm going to talk for today is trying to study the relation between Instanton Floer homology and the Heegaard diagrams of suture manifold. So let me just say my main result conceptually. Of course, I will give a more precise statement later. So giving a balanced suture manifold, gamma, right? So we can find some combinatorial data from its Heegaard diagram. That bounds the dimension of the suture Instanton Floer homology from above. Right. So as I said, I will make a more precise statement for this result later. First, let me talk about motivations. Right. So why would us care about the relation between the Heegaard diagrams and the Instanton Floer homology? Of course, well, there's one philosophy that for the Heegaard diagrams that describe and also determines the three manifold, and our Instanton Floer homology is an invariant for that three manifold. So there should be some relation between the two objects which are implicit. And second, well, so the Instanton Floer homology defined for any of these versions. So the structured Instanton Floer homology defined here usually comes from a set of partial differential equations. So Instanton Floer homology is hard to compute. So in general, you cannot expect to solve that related partial differential equation and compute the Instanton Floer homology from the construction. So we need some tools which can help us better understanding this topic. And the second motivation, which I would like to spend more time to explain, is we not only have this Instanton Floer homology, but also have many other versions of Floer series, and we also want to study the relation between them. So for homology, so there are four major branches of Floer series. Well, the first is the Instanton Floer homology. Of course, it's introduced by Floer, I think back in 1988. And second, well, we have the Heegaard Floer homology, introduced by also Gables, I think around 2003 or 2004. So also we have the multiple Floer homology. Introduced by Heegaard and Orpa. And they wrote a book on that in 2007. Also, we have the embedded contact homology. Which is introduced by Hutchins, I think around 2010. So all these four flavors of Floer theory, they have distinct constructions. So, for example, the Heegaard Floer homologies come from the Heegaard diagrams, and for multiple Floer homology and Instanton Floer homology come from two sets of partial differential equations, and embedded contact homology that come from contact geometry. So, although all these series have distinct constructions, we already know that three of them have been shown to be isomorphic. So all the rest, three. So just write a theorem in short that the Heegaard Floer theory have been shown to be isomorphic to the monopole theory and also the ECH. I think that's a work of many groups of people. And also, right, so because the Instanton theory here is kind of like isolated, we don't know if Instanton homology is also isomorphic to the rest. So a natural question to ask is, how about this Instanton Floer homology? Okay, so there is a conjecture by Kronheimer and Merkel, which says, well, the Instanton Floer homology should also be isomorphic to the proper version of the homology theory in other branches. So the conjecture that is we have let's just say for any balanced structure manifold. M and gamma. right? So we should have the superior Instanton Floer homology of this and gamma, which is a complex, finite-dimensional complex vector space, and this should be isomorphic to SFH of M and gamma, as using complex coefficients. And this is the future Floer homology in Heegaard Floer theory that is defined by Heegaard. And already this homology is defined with integral coefficients that we can use using complex coefficients to make those things complex vector spaces. And we know, well, here for Instanton theory, right? So the so we can use suture Floer homology to define Instanton Floer homology for a closed manifold. So as a corollary to that big conjecture, we also have that the Instanton Floer homology and the for closer manifold or for not, it should be isomorphic to the corresponding version of the Heegaard Floer theory. So they're the half version of Heegaard Floer theory introduced by Oswald and Saveliev. Okay, so this kind of like provides motivation that we want to study the relation between the Instanton Floer homology and the Heegaard diagram, because the Heegaard Floer theory, this is constructed based on the Heegaard diagrams. So I would like to make a comment here. So remark, so here this complex coefficient is kind of important. So maybe let me write here. So let me write it this way. So this future Instanton Floer homology for a balanced suture manifold, this requires the complex coefficients. But if you just want to define the corresponding version for closed ring manifold or for not, we have alternative definitions. But we have alternative definitions for I sharp and KHI, which can use other coefficients. And this is forward for first half, so there are portions for I sharp apply with integral coefficients, or also with the coefficients, and Fan will tell us more about that after my talk. But as a contrast, however, I believe, well, up to my knowledge, I should say, right. So if we are looking at the corresponding half version of Heegaard Floer homology, this is to not known example. Right, so there are many evidence for us to believe that for complex coefficients, the two theories are indeed isomorphic, and they have kind of like identical behaviors. But however, if we change the coefficients, if we look at integral coefficients, then there are actual torsion behavior for Instanton theory, which is not observed currently in the Heegaard Floer side. So first we're focusing on this complex coefficients, and let's see. So next I'm going to say more to present my theorem here. Any questions? Yes.
you remind us why the complex coefficient? You needed to define sutures?
Yes. Yes.
Remind us.
Right. Oh, yeah. So the reason is that, well, in order to define the suture incident Floer homology, the original construction is on closed ring manifold. So here, this M is a string manifold with boundary. So essentially, what we need to do is we glue another string manifold whose boundary is also the boundary of M, and so to close M, and we get a closed ring manifold. But however, we not only just look at the total homology group, but also there is a surface inside that closed ring manifold, and we need to take a specific generalized space with associated to an operator associated to that surface. And so because we take that generalized eigenspace, we need complex coefficient. Yeah. So right. So but we can use other definitions for the corresponding homology for closed ring manifold or not, and so that we can get rid of this eigenspace construct, so that we have other coefficients. Other questions? All right. So right. So before I state my main theorem again, so let me just quickly recall how the Heegaard diagram works for the suture manifold. So let's see the Heegaard diagrams. Right. So Heegaard diagram, let's just say we're given a balanced suture manifold. M and gamma, and a sutured Heegaard diagram is a triple, right? So we have sigma, alpha, and beta, where the sigma is a compact oriented surface with boundary. And we have two sets of disjoint curves, alpha and beta. Right, so I'm not going to say too much about how this data is constructed from the suture manifold, but essentially, if we just want to recover the suture manifold from this data, what we do is that our string manifold is actually a thickening of the surface, and then union two handles, and then we glue two handles on one side along those alpha curves, and we glue two handles on the other side along those beta curves. So I just say using alpha handles and union beta handles. Right, and our suture gamma, this is just a boundary of our Heegaard surface. And 1 times sigma, well, after gluing those one handles, the remaining boundary part, the remaining part becomes R plus, and the other part becomes R minus, which are those boundaries divided by gamma. So for any balanced suture manifold, we can always find many suture Heegaard diagrams. And so let me make a notation. Right, so for a balanced suture manifold, we define P of M and gamma to be the minimum of an intersection, which I'll write here, and I'll explain for a moment. Any this. Right. So if we're given this data sigma, alpha, and beta, so we can have two Lagranges, T alpha and T beta inside the K symmetric power of sigma. Right. So we can just look at the number of intersections between those two Tauri T alpha and T beta, and we pick a minimum intersection number among all possible admissible Heegaard diagrams of the suture manifold. Of the suture manifold. So here it is admissible. This is a technical condition which enable us to construct the suture Heegaard Floer homology. The suture Floer homology out of the state of I'm not going to say the details of the definition. But essentially, right? So so essentially, if we just have a balanced suture manifold and an admissible Heegaard diagrams, then we can construct the suture Floer homology, and this Chern complex is generated by T alpha and the intersection of T alpha and T beta. So essentially, so this T of M and gamma here just tells us the minimal number of generators in any possible Chern complex for the suture Floer homology. And now it's time to state our main theorem again. That giving a balanced suture manifold, and then gamma, we have an inequality. So the dimension is at most this number T of M gamma coming from counting the intersection point of this two Tauri here and T beta in any possible admissible Heegaard diagrams. So, any questions? Yes.
So, like, you would expect a lower bound from like the Triad origin of
Yes.
the Heegaard diagram, you know, sort of the design count of the intersection point as well, but sort of relative policy. But somebody, I mean, I know you and Lynn did this for the Alexander polynomial,
Right.
but that's enough for kind of generalized general suture manifolds.
Yes, that's a good thing. Yes, actually, right. That's another work by me and Ben. So we proved that for any balanced suture manifold, and of course, well, in our setup, if we have a basis for the second homology, relative homology of M, we can define a Zion grading where N is a rank of the second relative homology, and there is also like an Euler characteristic which we can associate it to each graded part. So we have a graded Euler characteristic, and that number is associated with Ferrari Pavilion, as you just mentioned. Yeah, so indeed there is a lower bound coming from the Euler characteristic. Yes, that is true. All right. Other questions? Okay, so right, let me make some remarks. So of course, every time we got an inequality like this, we would like to say, well, whether this thing can achieve equality or not, or how good this bound is. So at least for some cases, well, this inequality can indeed be sharp. So there are a few cases. That's now differential. Right. So as I said, well, this TR vectors actually make us give us the generators of the Chern complex for suture Floer homology, and for some special cases, all this homology, this Chern complex has zero differential. So two big classes of examples. So the first one is what is called the strong L spaces. And this is introduced by Grenier and Levine. I think around 2014. So essentially, this is just like a class of three manifolds which to make some good Heegaard diagram, so that using that particular Heegaard diagram, you can see there's no differentials. And so, as I just mentioned, well, there's a lower bound for the suture Instanton Floer homology that coming from all that characteristic. And in this particular case, well, this upper bound and lower bound actually coincide. So what we can conclude is that for any strong L space, Y, we have this equality holds. So the dimension of sutured Instanton Floer homology of M and gamma, that is the same as in this use. The two coefficients. You got 4. Oh, sorry. I should say, because it's a closed free manifold, so I use the corresponding version for it. And the second type is that if we have one mass inside length spaces. The one mass can be sort of like the generalization of two-bridge knot in 3 spheres. One knot in length spaces. And 3. Okay, inside Y, where Y of course is a length space where S3. So this one knot is kind of like if we have a Jenkins one Heegaard diagrams of Y, then this knot should be a trivial arc inside each of the antibodies. So this is kind of like a generalization of two-bridge knot. So, and as a corollary, so for any one knot, let's see K inside Y, we have this time we use the Instanton homology here, this dimension. Right, that is at most the dimension of the corresponding Heegaard Floer homology of the knot. Next version of the knot Floer homology. And right, so here we only have this inequality because, well, the lower bound coming from the lateral is not always sharp. But however, for many examples, it could be sharp. For any power snap, for example, for power snap, in F3, we have an inequality here. So even for power snap, this result is not known before. So there are only some partial results. From Henry Morocco, who used this spectrum sequence, giving us an upper bound for the dimension of Instanton Floer homology. And also, there is, okay, should look. And there's also work from Helen, Carroll, and Kirk who study kind of like the representations of the knot group of power snap, which can give us an explicit set of generators for this Instanton Floer homology group, which could give us better upper bounds than the one coming from the spectral sequences. But using our theorem, we can indeed achieve an equality for any power snap here.
Why don't you recall that? Why don't you recall the 1, 1 now?
Oh, for inequality here, yeah. So essentially, there's a very good Heegaard diagrams for 1, 1 half where the differential is actually 0. And so so the right hand side just descends to the homology, the dimension of the homology, and that's why the inequality occurs. And so on the other side, we have the Alexander polynomial for the Instanton Floer homology, which provides a lower bound. But in general, for all there are some low nuts where this lower bound is not achieved. So it just only have an inequality. But for those torus nuts, we know this. We know the Heegaard Floer. We know this non-Floer homology is actually determined by the Alexander polynomial of those nuts, and so this inequality becomes sharp. Other questions? All right, so let me see. Yeah, still have some time. So let me try to explain the proofs for our main theorem ideas. So let's recall the statement. So let's say we're giving a balanced integer manifold.
I'm still confused about the order. So I mean, 1, 1 not having a diagram. You're saying for Instanton version, the differential vanished, right?
Oh, I mean for Heegaard Floer version.
Okay. I thought.
Yeah.
I looked at the when they're.
Yeah, this is the the chain complex for the SFH of M and gamma, and this is the one introduced by Heegaard. Sorry, I did that. Okay. Yeah. So always we have some good things on the right hand side of that inequality, which give us a better result.
Yeah. What about the complements of homogeneous hyper surfaces alternating knots?
That's a good question. So I haven't thought about that yet, but maybe
that might engage the origin.
I see. So maybe I'll already
maybe that kind of
effort automating that.
maybe.
Yeah. Great. So I'll have a chat on that. All right. So other more questions? Yeah. So let me sketch the idea of the proof. So now we're doing a balanced integer manifold, and let's say for the convergence of the proof. So let me assume it has a very good Heegaard diagram. So let's and we have sigma, alpha, and beta to be well, let's see. So yeah. So let me only say a simpler cases. So let's say given closed ring manifold. Y and giving it its Heegaard diagram beta, so that what we have is that let's see, any component, any region of sigma minus right. So yeah, so for simplicity, let's just only chat the case for a closed ring manifold, but proof for a general suture manifold is a similarity. So what we got is that we right now we still have a Heegaard diagram, but this time this sigma has genus G, and alpha and beta they're just a set of G many curves. Sigma is closed in this case. Okay, so now there's a very important tools for us to deal with the situation is called the tangles. Right, so what we do here is that, well, our assumption is that the complement of those upper curves and beta curves on sigma consists of just this. So what we can do is we can pick one point in each region of sigma minus 1 minus and call them, let's say label them as P1 up to P. Okay. So now, so if we want to recover the three manifold Y out of the Heegaard diagram, what we do is we thickening. If we make a thickening of the sigma and then do alpha handles on one side and beta handles on the other side, and then the result will be our three manifold minus 2 3 balls. So this will be the thickening of sigma union alpha handles, and then union beta handles. So alpha handles are glued to 1 times sigma along alpha curves, and beta handles are glued to -1 times the -1 times sigma along the beta curves. So now we have those tangles. So Ti, which is Pi cross let me say -1 1 cross Pi. Which are properly embedded in this 3 manifold minus 2 3 balls. So the boundary of those 2 3 balls, one come from 1 times sigma, and the other comes from -1 times sigma. So these are properly embedded. So Ti. And this Y minus B3 minus B3. So and now the first observation is that, right, so if we start with this 3 manifold of Y minus 2 3 balls, and we just remove one extra tangle, right? So Y minus B3 minus B3, and we just remove one extra tangle. Let's see the neighborhood of P1, and then we take a meridian of the tangle P1, right? So this tangle connects the 2 3 balls. So if we remove that extra tangle from this thing, what we get is exactly 3 manifold minus 1 3 ball. And the meridian of this tangle become a simple closed curve, connected simple closed curve on the boundary of that 2 sphere. And so as a result, the frame Instanton Floer homology of Y, this can be described as the suture Instanton Floer homology of this thing. Any questions for this step? Right, so now our idea is that for the Heegaard diagram, and we look at each region by removing all the alpha handles and beta handles, the alpha curves and beta curves, and we assume that each region is a disk, and we pick one point on each region, and it will become tangles inside the 3 manifold minus 2 3 balls. And if we just remove one tangle, we just get the suture manifold that defines the three-dimensional Floer homology. And so the next step is that we want to construct a suture manifold and then gamma out of this Heegaard diagram again, so that two things hold. The first thing is that the dimension of our chart of Y is at most the dimension of the future Instanton Floer homology of this newly constructed suture manifold. Yeah, I will explain how to construct it later, but I'm explaining how the main theorem is proved at the moment. Then second, we can also show that the dimension of this suture Instanton Floer homology is the same of counting T alpha intersecting T beta. So this is the right hand side of the inequality. How we want to prove. So there are three things we need to do from now. The first thing is we want to construct this new suture manifold, and then we prove an inequality relating the three-dimensional Floer homology of Y, and then we also prove the inequality which relates this data coming from the Heegaard diagram, which is in our main theorem. So now construction of this new balanced suture manifold. Well, that's actually takes the idea here, right? So if we just remove one tangle, we just got the three manifold minus one single result, which defines the three-dimensional Floer homology. But now we have more tangles to remove, right? So we have 1 point or one tangle for each region as a complement of alpha and beta curves, so we can remove all the tangles. So our M is Y minus B3 minus B3. And then we're not removing just one tangle, but removing all the tangles. Where that is the same as we're having the thickening of our sigma and union alpha tangles and union beta tangles, and then with minus all the tangles, all the neighborhood of tangles. We can look at the manifold a little bit, because for the tangles Pi, they're coming from those points in the complements of alpha and beta tangles, so we can put it as in this way. Right, so those points are picked from the complements of alpha curves and beta curves. Right. And so because we pick one for each alpha and beta curve, so the idea is like, well, we have our sigma, and we have some alpha curves and beta curves. So now we have 1 point in each region of the complement of alpha and beta. Right, so you can imagine here, right? So if we remove this point, so it can sprint back to a neighborhood of alpha and beta curves. So it becomes cross a neighborhood of alpha union beta and union alpha handles, and then union beta. Right, so if we remove this P1 out of sigma, right, so we got kind of like an annular here, and then it brings back to a neighborhood of alpha curves and beta curves. And that happens for each region. And so finally, right, so if we remove all the base point here out of sigma, we just bring back to a neighborhood of all the and so then there is a theorem which is proved by Ben and I, which verifies the first inequality. So here it is gamma. Right, so it's the same as we pick the meridian of one handle here. So we just pick a meridian, one meridian for each handle. So mu I is a meridian of Pi. So after we construct the super manifold and gamma by removing all the tangles and then take meridian as the switchers. So we need to prove two things, right? So the first is that the Brinton Floer homology is at most the switchers in the Floer homology of that new super manifold and gamma. And the second, we need to compute examination, which gives us intersections, number of intersections between PR and beta. So for the first part, right, so this inequality, this is a theorem by proved by myself and Ben, which says, well, every time we remove one extra tangle, actually we need to increase the dimension of the corresponding suture Instanton Floer homology. So right, so if we just have one tangle removed, we got a Brinton Floer homology, but this M and gamma, this is obtained by removing more tangles. And each time we remove one more tangle, we must increase the dimension of the corresponding suture Floer homology. So the last thing is to really compute the suture Floer homology of this particular suture manifold here. So M and gamma. So to compute. Any questions? Can you state that again? Oh yeah, so the more precise statement is that every time we remove a tangle and then add the meridian of that tangle into the sutures, we need to increase the dimension of the corresponding suture Floer homology. Yeah, so we got the Brinton Floer homology by just removing one tangle, but we got M and gamma by removing more tangles. So that increased the dimension of the suture Floer homology. So we got this inequality.
But it doesn't necessarily.
Yeah, sometimes it could be this equality. Yes. Okay, so So in order to compute the suture Instanton Floer homology of this particular suture manifold, we need to go back to this description here, right? So as I said, well, if we remove all those tangles, the remaining part on the surface sigma is just the neighborhood of the alpha and beta curves, and we just make a thickening of that neighborhood, and then we attach alpha handle from one side and attaching beta handle from the other side. So what we can do is we can look at, right, so in this picture, right, this picture, we only have a neighborhood of this blue and red lines. And so we attach outer handles from above and attaching base handles from below, right? So if we just look at the neighborhood of one intersection between arc and base curves, then what we have here is that, well, let me draw this picture again. So arc handles, base handles. So what we have is that always attaching arc handle from above and base handle from below. So a rough picture looks like that. You're attaching this. You're attaching other base handles from below. So then actually we have those alpha and beta curves. This is the alpha curve. And we also have the beta curve. So this alpha handle and beta handle, they're kind of like attached together along a region here. And this is the disk. So if we kind of like decompose the three manifolds along that disk, we kind of like separate the alpha handle and beta handle along that one particular intersection. So our observation is that there is a disk for each intersection of alpha and beta curves. So we call them, label them, let's see, B1 up to Bm. And so if we look at the complement, there's a disjoint union of alpha handles and the disjoint union of beta handles. But each handle is just a three ball, which means, well, we find a set of disks after decomposing the three manifold along those disks, we just got a disjoint union of three balls, right? So which means, well, our M is actually a handle body, and those disks are kind of like present disks. And the next, well, this tells us the result for three manifold, and we also look at the sutures. So let's go back to the picture here. Right, so those points are the base points, and those points are what we removed, and our suture is just a meridian for each point. Right, so you can see what the disk is here. And this disk will intersect the suture exactly 4 times. Okay. And so I intersect the suture gamma 4 times for any disk. So this is a very special case where our suture manifold is a handle body, and it has a set of disks which decompose that handle body into a set of disjoint three balls, and the suture intersects each disk in 4 times. And in this case, so we can compute the future Instanton Floer homology where future manifold decompositions. So essentially, we along. So we're not only need to do the decomposition along DI, but also the orientation reversal of each disk. So you can see there are n disks. So there are 2 to the n power different cases we need to study. Each time we got different union of 3 balls with some sutures of 3 balls, and that either contribute 1 dimension or 0 dimension to the suture Floer homology. And we can do this count, and finally, the number of times where we got 1 equals well the intersection number of alpha and beta for the suture Floer homology. So it's actually we just got equality here. So the dimension actually equals the number of intersections of this P alpha and P beta. So I don't have more time to explain how this count really works, but I will stop here. Thanks.